Hey everyone, welcome to The Explainer. Today, we're taking a really fun, practitioner-focused journey into the actual physics of sight. Think about it for a second. If you've ever worn glasses or, even just looked through a camera viewfinder, you have directly benefited from the incredible physics of light. But instead of just looking at abstract physics equations, we're going to look at this through the lens, pun entirely intended, of an optician. We're going to break down the exact principles, the physical tools, and the math used to literally bend the universe just to fix your vision. Okay, so let's dive right into this. We see these numbers all the time. Maybe you actually have a piece of paper from your eye doctor sitting around right now with a plus 2.00 or a minus 1.50 scribbled on it. To most of us, that's just a blurry medical code, right? But to an optician, these common, everyday numbers are actually the ultimate mathematical solution to a highly complex physics puzzle. Those numbers represent the exact amount of optical force required to bend light rays so they perfectly hit the back of your eye. But to understand how we get to that single elegant number, we first have to understand the fundamental behavior of the light itself. So, let's start with Section 1, the rules of light. Before an optician can even think about crafting a lens to fix your vision, they need to understand exactly how light behaves in the wild. Light is a form of electromagnetic radiation, and naturally it travels in perfectly straight lines. And in a vacuum, it travels at an absolutely staggering speed. We're talking 300 million meters per second. That is literally the universal speed limit. But here's where the optician's job actually begins. Light only travels in those perfectly straight, uninterrupted lines when it's in a homogeneous medium. When we deliberately introduce a new material into light's path, like, say, the transparent glass of a spectacle lens, we intentionally force that light to slow down. And when light slows down, its path changes. Which brings us to Section 2, refraction and optical density. Let's look at the mechanics of exactly how that light bends. When light passes from one medium into another medium that has a different optical density, the light rays bend. This phenomenon is called refraction. Scientists and opticians use something called Snell's law to really understand it. Snell's law essentially states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. And that constant, that gives us the refractive index. It's a precise mathematical measure of exactly how much a specific medium puts the brakes on light compared to a vacuum. To put that into perspective, let's look at the exact numbers an optician is calculating against. A vacuum is our ultimate baseline, sitting at exactly 1.0. Air is practically the same, just a tiny fraction over 1.0. But notice the stark jump when light goes from air to glass? It jumps to an index of 1.5. The rule here is that the greater the difference in optical density between two materials, the greater the bending of the light. So if you were to pass light through a diamond, which has a massive index of 2.42, it would slow down dramatically and bend incredibly sharply. When an optician is working with a standard glass lens, they are constantly calculating for that exact transition from the air around you at 1.0 right into that glass at 1.5. Moving right along to Section 3, tools of the trade. So how do we actually harness these universal laws? Well, it brilliantly comes down to the fundamental difference between mirrors and lenses. Mirrors rely entirely on the phenomenon of reflection. They just bounce light back from a surface, usually using a polished, reflective metal. Because the light just bounces right off the surface, the physical thickness of a mirror doesn't affect its optical function at all. It just doesn't matter. But lenses, which are the optician's absolute bread and butter, are fundamentally different. They rely on the phenomenon of refraction that we just talked about. They use transparent materials like glass, and because the light has to actively travel through that material, the physical thickness and the curvature of that glass is absolutely critical for its function. Let's dig deeper into that in Section 4, Mastering Spherical Lenses. Knowing that thickness and shape are literally everything, we have to look at the two primary shapes used to correct vision. Every spherical lens is bounded by two curved surfaces, and they basically fall into two main categories. First up, we have convex lenses. These kind of bulge outward on both sides, making them thicker at the center and much thinner at the edges. Because of this specific shape, when parallel light rays pass through it, the convex lens acts as a converging lens. It forces all those light rays to bend inward, coming together toward a single principal focus point. On the flip side, we have concave lenses. These curve inward on both sides, meaning they're thinner at the center and thicker at the edges. This does the exact opposite. It's a diverging lens, actively forcing those light rays to spread away from each other. So, how in the world do we write all this down on a tiny prescription pad?
We use a universal sign convention. Convex equals positive and concave equals negative. And this isn't just some arbitrary rules someone made up, it's entirely based on how we measure distances along the principal axis of the lens. Because a convex lens converges light to a real focal point on the other side of the lens, meaning in the direction the light is already traveling, its focal length is measured as a positive number. A concave lens, however, diverges light, so its focal point is actually virtual. It appears to come from behind the lens, completely against the direction of light, therefore its focal length gets a negative sign. This is the secret code of the optician.
Now for the grand finale, Section 5, the power of a lens. This is where we pull all of these physical properties together into a single, highly useful metric. We've talked about refraction, optical density, lens shapes, and focal lengths. But an optician ultimately needs to communicate the true strength of a lens in a single actionable number. This is called the power of a lens. It's quite simply defined as the ability of a lens to converge or diverge light rays. It's that straightforward. The greater the power, the stronger the lens, and the more sharply it bends the light passing through it. And here is the elegant little formula that ties the whole shebang together. P equals 1 divided by F. Power equals 1 over the focal length. But, and this is absolutely crucial, notice the units. That focal length must be measured in meters. When you divide the number 1 by the focal length in meters, you get the power in a unit called diopters, which is represented by a capital D. This inversely proportional relationship is just fascinating. Think about it. If you have a very short focal length, meaning the lens bends the light super sharply over a very short distance, the denominator is small. That makes the overall power, or the diopters, much larger. So a shorter focal length creates a much stronger, more powerful lens. But what happens when we introduce a little real-world complexity? Sometimes a single lens just isn't enough to correct a tricky vision issue. Well, when an optician stacks multiple lenses so they're in physical contact with one another, calculating the final power is actually beautifully straightforward. You simply add them together algebraically. The total power P is just P1 plus P2 plus P3. So, if you were to combine a convex lens with a power of plus 2.0 diopters and a concave lens with a power of minus 0.5 diopters, the combined lens system has a net power of plus 1.5 diopters. It's simple math that allows practitioners to incredibly fine-tune a final perfect prescription. When you master calculating diopters like this, you can actively solve huge real-world problems. Just look at how widely these exact formulas are applied every single day. To correct myopia, which is short-sightedness, an optician will calculate the perfect negative power concave lens to diverge the light just enough before it even hits your eye. If you need a simple magnifying glass, well, you're using a convex lens to create an erect, magnified, virtual image. These exact same laws of refraction and lens power calculations are used to design complex camera lenses, the high-tech objective lenses in microscopes, and even those wide-angle peephole viewers you look through on a front door. Every bit of it, comes back to P equals 1 over F. Which really leaves us with this final thought to chew on. Take a second and just look around you. If you're wearing glasses right now, or even just looking at this explainer through the complex glass lenses of a smartphone or a computer monitor, how is your daily view of the world being subtly shaped by calculated optical densities and carefully engineered focal lengths right at this very moment? It's pretty wild to think about. Every clear image you see through a device is a total triumph of physics. Thank you so much for joining me on this explainer. I really hope you never look at a piece of curved glass the exact same way again. Catch you next time.